You ever wonder what's really holding our digital world together? I mean, it's not just cables and servers, right? It's something way more fundamental. It's agreement. And when that agreement shatters, well, so does everything else.
So, let's start with a little riddle. What in the world does a massive Cloudflare outage, the kind that takes down a huge chunk of the internet, have in common with the Solana blockchain just freezing solid for hours? They seem like they're from different planets, but nope. They were both victims of the exact same deep-seated problem.
And that problem? It all boils down to one single, incredibly difficult challenge: getting a bunch of computers to agree on something. Because when they can't, the results can be, well, a total disaster.
Just look at Solana. We're talking about more than 150 hours of total downtime. That is over 6 full days where a multi-billion-dollar network was completely paralyzed. All because its computers just couldn't get on the same page about the state of the network.
And listen, this isn't some niche crypto thing. A gigantic Cloudflare outage was tracked all the way back to a single, tiny bug in the system they used to get their computers to agree with each other. And when you remember that companies like Cloudflare are basically the foundation the modern web is built on, you start to realize just how fragile this whole thing can be. So this brings us to the core idea here: distributed consensus. It's basically the magic trick of making a whole fleet of independent computers act like one single, super dependable machine. They all have to agree on the exact same history of events in the exact same order, even if some of them crash or the network goes haywire.
Now, this is not a new problem. For decades, some of the sharpest minds of computer science have been on this epic quest to solve it once and for all. For the longest time, the undisputed champion was an algorithm called Paxos. And it was revolutionary. I mean, truly powerful, truly fault-tolerant. But it had this one giant, glaring catch that kept it from taking over the world.
And here's the catch. In the words of the very researchers who would later create its replacement, Paxos is just exceptionally difficult to understand. It was so complex, so subtle, that almost nobody could actually build it correctly. Which, you can imagine, is a pretty massive issue when you're trying to build the most critical systems on the planet.
So, all that frustration led to a breakthrough. If the biggest problem was that the algorithm was impossible to understand, then maybe the solution was to design a new one, where being easy to understand was the #1 goal. And that's where RAFT comes in.
So back in 2013, 2 researchers, Diego Ongaro and John Ousterhout, they decided to attack this problem from a completely different angle. Their main goal wasn't just performance or correctness, it was understandability. They wanted to create an algorithm that was not only solid, but one where you could actually see why it was solid. And what they came up with was RAFT.
And the difference in philosophy between the two is just night and day. Paxos is what we call symmetric. Every computer is an equal peer, which sounds nice, but it gets complicated. RAFT, on the other hand, is asymmetric. It says, nope, we're going to have one strong leader at a time. Paxos is dense, it's subtle. RAFT is broken down into simpler, easier to swallow pieces, like electing a leader and then replicating data. And that focus on simplicity, it changes everything.
You can see this simplicity in how RAFT elects a leader. It's kind of like a real election. So every computer, or node, starts out as a follower. Each one has its own little random timer. If a follower doesn't hear from the current leader before its timer dings, it just assumes the leader is down. So it flips into candidate mode and shouts out to all the other nodes, hey, vote for me. If it gets votes from a majority of the group, boom, it becomes the new leader. Simple, right? And that little random timer? That's the secret sauce that stops everybody from trying to start an election all at once.
Okay, so once it's elected, the leader's job is basically to be the ultimate project manager. It takes total control of this thing called the replicated log, which is just a fancy name for a shared, ordered to-do list. Every single change, every update has to go through the leader first. No exceptions.
So how does the leader keep everyone in line? Well, picture this. A client sends a new command, like update this value. The leader's the first one to write it down in its own lock. Then it sends that update out to all its followers. And it just waits. It doesn't do anything else until a majority of those followers write back and say, yep, got it, stored it. Only then does the leader mark that command as committed, locked in, permanent. This simple majority rule is what guarantees that every single machine ends up with the exact same history in the exact same order.
So RAFT is this beautiful, understandable algorithm. Problem solved, right? The internet is safe forever. Yeah, not quite. The theory is elegant, but reality, as always, is messy. Which brings us right back to where we started. If we have this fantastic algorithm that's used by huge systems like Cloudflare, Kubernetes, and tons of databases, why do we still see these epic failures?
And the answer is so important. An algorithm on a whiteboard is not the same thing as thousands of lines of code running out in the wild. That huge Cloudflare outage, it wasn't a flaw in the RAFT theory, it was a bug in their specific code that implemented RAFT. A perfect blueprint can't save you from a tiny mistake in the construction.
So now we have a whole new problem. How do you find these little ticking time bombs hidden in the code before they blow up your entire system? Well, you have to get aggressive. You have to torture test it.
And that's where amazing new tools like consensus stress come into play. Think of it as a professional chaos muppet for your distributed system. It's a testing framework that is specifically designed to be an absolute nightmare for the system. It deliberately slows the network to a crawl, it cuts off communication between computers, it crashes them at the worst possible second, all to find those hidden bugs before your customers do. And at the core of this thing is what's called an attacker controller, and it acts like an evil genius. It commands these little attacker clients to run alongside your system and just create targeted mayhem, like severing a network connection right as the leader is being elected or crashing a node just after it received a critical piece of data. The whole point is to simulate the worst possible day your network could ever have over and over in a safe place until it's basically unbreakable.
And does it work? Oh yeah. In its very first run, Consensus Stress found more than 10 brand new, serious bugs in public, widely used open-source consensus systems. These were vulnerabilities just sitting there, waiting to become the next big headline.
And that's the real takeaway here. Building the reliable digital world we all count on isn't just about having a brilliant idea like RAFT. That's only half the story. The other half is the hard, grueling work of relentless, sophisticated testing to make sure our code actually lives up to the beauty of the theory.
And when we get this right, the impact is just huge, and it goes way beyond data centers. The exact same ideas about agreement that keep the internet from falling apart are now being used to solve problems in the physical world, like getting swarms of robots to move in perfect, synchronized formation. It's the same fundamental problem, just played out with atoms instead of bits.
Which leaves us with one final thought. Our whole digital civilization is built on this foundation of algorithms that help computers agree. Our money, our power grids, our communication. The real challenge isn't just inventing these algorithms, but making absolutely sure through constant paranoid testing that they never, ever fall apart when we need them the most.